Okay, so now let's look at how sound waves travel. And there's quite a lot of technical stuff in this. So again, pause the video if you need to make some little notes and think it through. It's no good moving on if you don't understand what we've covered already. So I've set up on the desk here a slinky spring, and it's not the easiest of things to film in a rush, but let's see what we can do here. Okay, and the slinky spring is the material that carries the sound wave. It's behaving like the material that carries the sound wave. So between my mouth and vocal cords that are vibrating and the microphone on the top of my camera is air. Air is called the medium. So there's your first word, medium, the thing that sits between that carries the wave energy. Earthquake, the medium is the earth. If you make a squeaky noise or clap your hands or try to underwater, I remember when I was teaching diving, we used to get a piece of metal and bang it to try and get people's attention underwater, or a ball bearing in a metal thing and shake it and they heard the clicking sound. The medium then is the water. Okay, so you need a material to carry a sound wave. Now, I've set up the slinky here, and the slinky represents the air. So air is basically made of nitrogen and some oxygen molecules, and each coil of the spring, each coil that you see, okay, each turn more correctly, represents maybe a molecule of air, a molecule of nitrogen. And it's what you guys all do in the lunch queue if you're getting annoyed or coming in and out of chapel, though you're usually very well behaved. If one person pushes, that pushes the next person and the next and the next and the next and the next. My students call it a sort of Mexican wave. And so the way we're going to get sound to move is we're going to get one particle to push forwards, to push the next and to push the next. Now, before I demonstrate that, on the oscilloscope, you saw wiggly waves like this, though they were sort of facing you like that. Okay, that's a mathematical or electrical representation of a sound wave. Okay, but in reality, let's think of it properly. If I put my loudspeaker here, it's going to do this. It's going to come backwards and forwards. It's going to come towards you and away from you. The tuning fork is going to vibrate towards you and away from you. So it's going to vibrate the air backwards and forwards. Okay, right, so let's get started. Got the slinky spring. Okay, and I'm going to send the representation of a sound wave to the clanger teddy bear that's at that end. Okay, so there we go. And I'll do it a few times. Forget the noise from the desk, but it proves there's some energy travelling. But what you'll notice is I send a pulse. So I go like that. And you'll see that that pulse hits the far end and it reflects back. And if it reflects this room, okay, we call that an echo. Yeah, an echo. Sound reflecting off a hard surface is an echo. And if I close all the curtains, these black curtains absorb the sound energy, and so we don't get an echo. So some recording studios have lots of soft material and things like that, and foam and stuff in the walls to absorb the sound waves, so we don't get reflections, we don't get echoes. Okay, so what you should be seeing here is that pulse going down. Look at the slinky. Okay, look at the slinky. It's still here. So when we send a sound wave, I'm not sending air to you. Okay, otherwise I'd run out of air and I'd kind of be unable to breathe. I'm shaking this bit of air, that's shaking that bit, that's shaking this bit, and that's why it takes time to travel. So if I push forwards, these coils are going to compress. They're then going to expand, rarefy, compress the next ones, compress the next ones. So a sound wave is a series of pulses that are travelling, okay, and they consist of compressions and rarefactions, spreading out, okay, technical term there. So there you go. There are sound pulses going up and down, okay. Now it's important you notice that the slinky isn't moving from side to side. Neither is the slinky moving up to that far end. Okay, it's this push-pull action that is the sound wave. Okay, and it's got a name. So get ready for this. It's a difficult one for most students to remember. It's called a longitudinal wave. A longitudinal wave. Okay, so sound waves, learn it for GCSE, are longitudinal waves, and that's where the vibration or oscillation that produces the wave is parallel to the direction that the wave travels. Okay, so I'm moving my hand up and down parallel to the way the wave travels. And a sound wave consists of a series of compressions and refractions, rarefactions spreading out of a medium. So I'll just say that again. Sound wave is a longitudinal wave, and it consists of compressions and rarefactions of a material that carries the wave, in this case the slinky, okay, and that's the medium. But I wonder what happens if we didn't have the slinky. So that's what I want to think about next. So remember, the slinky here is the medium, the thing that carries the wave. There it is, travelling. Okay, the desk is the medium, the thing that carries the wave. And the air between me and the microphone is the medium that carries the wave. But you might have heard, if you scream in space, no one will hear you. Okay, or versions of that. And it's really true. Okay, so when you're on the moon, who knows? Some of you guys might actually, when you grow up, be astronauts and are long since be gone, but maybe you'll be doing space travel because Mars is where we want to get to. But if you have a lunar base and you go out onto the moon's surface in your spacesuit, there is no way you just can't talk to another astronaut. There's no air between you. There's no medium. Yes, you could tap on each other's visors and the visor would vibrate and the air inside would vibrate. But if you were a distance apart, you'd talk and you wouldn't hear anything because there's no medium. Okay? In other words, there's nothing to vibrate, no medium to vibrate longitudinally in a vacuum. Okay? So, we've got to go off to the moon to demonstrate this, have we? Well, no, we haven't, because I can do it in the lab, okay? All I need to do is produce loud sounds, and I need to do it in a vacuum and see what you hear, okay? I don't think I'm spoiling it by saying if we produce loud sounds in a vacuum, loud sound, remember something vibrating and shaking with a high amplitude. If we do that, we won't hear a thing outside. Okay, so I'm going to put a link up now to my video of sound in vacuums. Go and have a watch of that, and I think you'll be really surprised by what happens. So I hope you got a chance to watch that video on sound in vacuums. It's really surprising, isn't it? That if there's no medium, you won't get any sound travelling at all. And this explains partly why sound takes time to travel, because the medium has to vibrate and pass on those vibrations, and that takes some time. So we talked earlier on about the fact that you can hit a cricket ball and the people watching hear the click later. Thunder and lightning pretty much happen at the same time. But of course what happens is the light goes and gets to you really fast, 300 million metres a second. Okay, and the poor old sound pressure wave caused by the lightning strike expanding the air rapidly because it heats it up only travels at about 300 metres per second. Okay, so it's 1 million times slower. So it's going to take a while for that sound to get to you. And I just want to end this section on saying something that's really important for you to know, and something that I was taught sort of incorrectly. That I was taught that if you see thunder and lightning, see the lightning, and then you count 1, 2, bang, 3 seconds. It must be 3 miles away. And then later on when we got metric system, lightning, 1, 2, bang, 3 seconds away. Oh, it must be 3 kilometres away. Okay? Everything I've just said there is complete rubbish. Okay? In fact, you're way closer than you thought. Okay, think about it. If sound travels at 300 metres per second, then it does 900 metres in 3 seconds, so about 1 kilometre. Okay, so if you see lightning, 1, 2, bang, that's 3 seconds you've had to wait. Okay, The lightning is only 900 meters away. Okay, it's only a kilometer or so away. So if you see the lightning strike and it goes bang after 1 second, you need to be really careful because you're only 300 meters away. You know, the sort of distance we've got in front of us here of the school playing fields. You're much, much closer than 1 mile or 1 kilometer that I was taught incorrectly, not by my teachers, I hasten to add, when I was at school. Great, so I hope you've got a really good understanding now from watching the videos of what sound is. It's an important topic in physics. As you can guess, there's probably so much more I can say and lots of stuff I've missed out, but I do hope I've covered the main things that you need to know. Anyway, make some notes and make sure you really understand it well. Maybe we should do some sound calculations at some stage and do a bit more of the maths. But until then, have a good time, and I'll see you then.